Hi, welcome to lesson 10. So we're going to talk about the goodness of fit test. So this is for a scenario where we have a one-way table. That is when we have a table for one categorical variable, and this categorical variable can have multiple categories, but we're just looking at one variable. So the example that we're going to use throughout lesson 10 is the M&M example. Honestly, this is pretty fun in person, in my opinion, but I'm a big fan of eating candy. We usually would bring bags of candy to recitation this week if we were on campus. So Mars Inc. is the company that makes M&M's candies, which come in multiple colors, and so they advertise on their website, and it's not super easy to find on there either, that the mix of their colors, so specifically the milk chocolate plain M&Ms, 13% of them will be brown, 13% will be red, 14% are yellow, 16% are green, 20% are orange, and 24% are blue. So, I mean, is that exactly what we're going to get in any given bag? Probably not, but that is the rough makeup of at least what they're advertising that they produce. So we go ahead, we take a bag of M&Ms. This one's actually a king size bag, otherwise it wouldn't have 60 in it. So we have a one-way table. It summarizes the count of each color that I got for this one bag. So I got 9 blue M&Ms, 8 orange, 12 green, 15 yellow, and so on. If I want to look at my sample proportion, so the proportion of the M&Ms in my bag that are blue, so P hat. So we have a hat here. Because it's from the sample, it's 9 out of 60, which is 0.15. So the company is claiming that 24% of all of their candies are blue. So what's up with there being 0.15 in this sample? You know, is that off enough to make alarm bells go off? Do I believe them or not? So the chi-square test for goodness of fit, one way we could be looking at it, we want to know, hey, do we have evidence that the proportion of M&Ms that are blue, is that different than the claimed 0.24? If we have it set up that way, you could have it so P blue is equal to 0.24. So this notation is just saying the proportion of all M&Ms that are blue. And then the alternative, we don't necessarily suspect one way or the other if it's higher or lower. We just want to know if it's different. And this is something we can do. This is a test we could run, but it's not a goodness of fit test. This won't actually give us much information about the distribution of the rest of the colors. This would be if we only want to test the proportion of M&Ms that are blue, whether or not it's claimed. We can get at, though, the proportion of M&Ms that are each of those colors all at once. So the scenario here, we like it to be a random sample. We like it to be a random sample because we want it to represent that larger population. It's for a categorical variable that has a certain number of categories, so k possible categories. So each outcome has its own likelihood, so each category has its own probability or proportion of showing up. So P1, P2, P3, all the way through PK, however many categories you have. So you can label them with numbers. If you do this, make sure that you have like 1 equals blue, 2 equals green, whatever it is, and so on. If you use number labels. I had P blue, that's totally fine. You wouldn't have to have labels because you are including them. So PI is the probability of the I outcome occurring. So just any given, it's a generic group. So the proportion for group I, and you can define it as whatever color you want, is the probability if you randomly selected an M&M of it coming up that particular color. And then it is important that we have independent observations. It's a little trickier when we have batches of things. In all honesty, we probably, with M&Ms, they make things in batches. So, but we're going to proceed as if we're okay here. You don't want one observation influencing another observation. Our goal is going to test the distribution, so that claim distribution of the categorical variable. So we're no longer testing just one group. We're testing all groups. So we have 6 colors here. We want to test the distribution of the 6 colors all at once. Is this distribution of colors that's claimed, so those 6 proportions they give us, is that distribution from Mars accurate, or is it off? Here is where things are going to change up a little bit from where we've been. So our null hypothesis will be, P1 is equal to whatever value, P2 is equal to whatever value, all the way through, so we have 6 categories. The alternative is saying, hey, at least one of them is different than what's claimed. At least one of them has a proportion that's different than what's claimed. It doesn't mean all of them, but at least one of them. Because if at least one of them's different, then that's enough for me to believe that the claim isn't quite right. So for our M&M example, write the null and alternative hypotheses. So note we have 6 categories or 6 colors. We have red, orange, yellow, green, blue, and brown. So we're going to need a P equals for all 6 of those. So my null, P blue is 0.24, P orange is 0.20, and so on. I'm going to include all 6 colors, and I'm going to have all these values. This is that claim from Mars, Inc. Right? So none of these values should come from your sample. There are no hats. That's really, really important details here. The alternative, just one of these is different than what's claimed. If at least one is, that's enough to convince me that that whole generic statement isn't necessarily true. So at least one of the PIs is incorrect. So the proportion of M&Ms that are a certain color, at least one of those colors it's not accurate. And just that notation wise, that P, and then I have a color name here, like P blue, it's the claimed population proportion. So the proportion of M&Ms that are that specific color. So just to review here, because we are, like before, we calculated either a z-test statistic or a t-test statistic. This week we're going to calculate what's called a chi-squared test statistic. Chi, it's spelled like C-H-I, but it's pronounced chi. It's a Greek letter, and that's not the best chi I've ever written. It's kind of like a curvy looking X. So chi-squared, it's going to look like this. Just as a review, we have this notation, this sigma xi. It means add all the x's together. So this means add or sum. If you see that notation in any of our classes, it means add things together. So in order to figure out whether or not the distribution that's claimed by Mars is good or bad or whatnot, we're wanting to compare what we observed in the actual sample, so the counts of colors we saw in the actual sample, versus what we would have expected to have seen. So specifically, if we had had a sample of 60 M&Ms and it was exactly what Mars bars claimed it is, how many would we have expected? So then we want to tell, okay, well, how far is what we observed from what we would have expected if the null is true? So the chi-square statistic, it's really a measure of how far what we actually observed in the sample is from what's claimed. And the formula for the statistic, which we're going to break down into parts, it's chi-squared is equal to, and then sum. So you're going to take the observed count minus the expected count, square it, because we want it positive, divided by the expected count, and then add that together for all 6 categories. So you're going to have 6 numbers that you add together. And we're going to break it down into a table so it's a little easier to see. And once again, there are ways to do this in the calculator. It probably is easier, but it is important to understand like how we're calculating it. So the chi-square test for goodness of fit, when it comes to the expected counts, we want to know if the null was true and we had the sample size that we actually have, which is 60 in this M&M scenario, how many would we have expected? And this isn't on average. If I just repeatedly took samples of 60, how many blues would I have expected? How many oranges would I have expected? And so on. So these numbers a lot of times are decimals, and that's okay because they are an average. On average, if I had, many samples of 60, I would have expected about this on average to be blue. Important condition. So one of the conditions to do the goodness of fit test is that the expected number for all of your categories need to be at least 5. You don't want to have any of those expected categories fewer than 5. It basically implies that you didn't have a big enough sample size that you would have expected to see at least 5 in each category. So then how you calculate your counts for your goodness of fit. So you're going to have however many categories you have, that's how many expected counts you're going to have. So if we have 6 colors, we're going to have 6 expected counts. So if I want the expected counts for category 1, I'm going to take that overall sample size, so like 60 in the M&M scenario, times probability or the proportion for group 1. So if I'm looking at blue, N times P blue, at least what's claimed, that's 60 times 0.24. That was, because this is not math I can do in my head real quick, 14.10. So what that's saying is if I were to repeatedly take samples, random samples of 60 M&Ms over and over and over, on average about 14.1 of them would be blue. And then I'm just going to wash, rinse, repeat. I'm going to do this for the second category, for the third category, all the way through the last category. And we just use that generic letter K. That's just to denote the last category. There have to be at least 2 categories. It's really, really not going to work out if there's not at least 2. But usually we're going to have more than 2. It's more likely we'll have 3 or more. And then similar to the T distribution, it's going to be important to define degrees of freedom. So degrees of freedom for what we're going to go into as a chi-square distribution, it's going to be the number of categories minus 1. So in the M&M example, we have 6 colors, so 6 categories minus 1. So we'll have 5 as our degrees of freedom for the M&M scenario. So going back to the M&M example, we want to go ahead and find our expected counts. So I'm going to fill them in here. So if I had 60 M&Ms and 24% are blue as claimed by the company, on average, I would have 14.1 blue out of 60. I'd have 12 even for orange, 9.6 green, 8.4 yellow, 7.8 red, and 7.8 brown. Things to note is observed, if I add these up, I should get to 60. Right, my sample size. If I add my expected counts, they should add to 60 as well. Something's gone sideways if they don't also add to the same sample size. Now we're going to break this down. I have a larger table to fill out. So like I said, if I add these across, I'll get 60. Fill in the expected values that we just calculated. If I add these across, I should get 60. So now I want what we actually observed in the sample minus the expected. So observed minus expected. So filling that in, 10 minus 7.8, that's 2.2. 8 minus 12, that's negative 4. So just keep in mind, if you're taking a smaller number minus a larger number, you get a negative number. It's not going to be the biggest deal after we square. That's going to be handy. So now we're going to take this observed minus expected and we're going to square them. But before I do, I want to note that so there were more reds observed than expected. But there were fewer oranges than expected. So some are above what was expected, some are below what was expected. If you were to add across here, you should add a 0. Because on average, you're hitting the mark. So some are above what's claimed, some are below what's claimed. But, I mean, it comes down to they can't all be above and they can't all be below. Otherwise, well, something went really horribly wrong with math. So then if I were to square these values, that's my next step here, plugging in. So just a note on notation, you're going to want to put anything, like if you're squaring a negative number, you want to put in parentheses, because negative 4 squared is like saying negative 1 times 4 squared, and that's negative 16, versus negative 4 squared. And that's positive 16. Just a notation thing. Because if you write it the one way, it's not quite right. So go ahead, square. Make sure that any value that you're squaring that's negative is in parentheses when you're squaring it. You should get all positive values, right? So if you square positive numbers, you get positive numbers. If you square negative numbers, you get positive numbers. So now they're all positive. And that's on purpose, because if we were to add and subtract the observed minus expected, some of them would cancel each other out, because some are positive, some are negative, and we don't want that. So then the last step is to take that observed minus expected squared and divide it by what was expected. So we want to know, well, how far away was what we observed from what we expected, but also take into account what did we actually expect. Did we expect it to be high or low? That matters too. If it's really different from what it ended up being claimed, it matters if the claim was really high, really low, somewhere in the middle, that kind of thing. So plugging those in, I rounded to 3 places past the decimal for these. If you put it in a calculator, it will not round at all. Just for the table is where I rounded here. And things to note, if I go ahead and I add these together, that's my chi-squared statistic. Just adding these together, that's my statistic. Things to note too is, if you look, this 0.621, that's how much the red is contributing to the chi-squared statistic. If you look at yellow is definitely contributing the most out of any individual color. Yellow and blue, but especially yellow. Those two colors contribute the most to the chi-squared statistic. What that means is those were the furthest from what we expected them to be. The yellow in particular was really different from what we expected it to be. If M&M colors are really distributed the way that Mars says they are. So out of all the colors, yellow contributed the most to the statistic. Blue contributed to. The others are pretty small. So calculating, we're just going to put it together now. So for blue, we're just going to put orange. Sorry for goofing up the order. I know we didn't stay in the same order every time. So absolutely, you can throw that into your calculator if you want. That is a lot of steps for me. I prefer breaking it down into the table. I am more accurate that way most of the time. It's a lot for me to put that much into a calculator at once. It's a really, really long line if you're trying to do that. So adding them up, it comes out to really close to 10. I think it was something like 9.9996 or something. So if you round to 3 places past the decimal, you're right at 10. So now that we have a chi-squared statistic, that's where we jump to saying, oh, well, we have a chi-squared distribution with these degrees of freedom and have a chi-squared table, just like we would with a t-test statistic and a t-table. But we need to stop and talk about chi-squared distributions real quick. So the p-value, whenever we perform a chi-squared test, it comes from comparing the right-hand area. So that upper probability. So the p-value is always going to be whatever your test statistic is. Ours is what, 10? It's going to be the area to the right. Although we don't have one with the same degrees of freedom as we need. So you can obtain a p-value. You can either use a calculator, or you can go ahead and you can use a chi-square table. Chi-square tables are a little more old school. It's pretty standard still for folks to be using a z-table or a t-table. Chi-square tables are becoming a little less commonplace, although they're extremely similar to using a t-table. So I'm sorry, I don't remember what the second bullet here is for. Chi-square distributions are a family of distributions. So chi-squared distributions, they are very right skewed. At least to start off with. And let me clarify what I mean there. Skewed. So if you look here, this top one, this, I don't know, is it gray? Degrees freedom 1. It looks like it pretty much just goes root. It pretty much just goes from high to low. It's very, very skewed right. If you go to degrees of freedom 4, it now has a peak right around here, but it's still pretty right skewed. If you increase the degrees of freedom to 8, it's still right skewed, but it's starting to get closer to a normal shape. So the higher your degrees of freedom, the closer to a normal distribution. Although practically, we're probably not likely to want to get really, really high degrees of freedom here for this particular scenario, if you think about it, because comparing like a distribution that has, 20 some odd categories, that can be really, really overwhelming just to think of, to wrap your head around. Doesn't mean that people don't. I'm just saying it might be a little hard to think about. So in particular, it's very similar to the t-distribution in that we define each chi-square distribution by its degrees of freedom. And in this scenario, it's number of categories minus 1. So, and that will tell us what it's shaped like. So the higher your degrees of freedom, the more normally shaped it's going to be. The lower your degrees of freedom, the more right skewed it's going to be. So for our chi-squared goodness of fit test, so back to the M&M example. We have a chi-squared statistic of roughly 10. So if we have a chi-square distribution of degrees of freedom 5, because number of categories minus 1, there are 6 colors, that's going to equal 5 here. We want this shaded blue area. That's going to be our p-value. So our degrees of freedom are 5. That tells me which row to use, similar to using the t-table. And then I'm going to look for my chi-squared statistic here. So like it's not between 8.12 and 9.24. It's between these two numbers, right? So 10 is between 9.24 and 11.07. So that means I'm going to go up and go, oh, well, my p-value is between these two numbers. Be careful to switch them so that it's your p-value is between 0.10 on that side and 0.05. You don't want to say that your p-value is greater than 0.10 and less than 0.05 because that won't make sense. So our test statistic falls there. Therefore, our p-value is between 0.05 and 0.10. And this is where it's important to remember, well, what was my significance level? And just a reminder, it was mentioned, but really just very quietly, 0.10. So if my p-value is between these two numbers, I know that it's less than 0.10. It's not equal to 0.10, it's less than it. So that's enough information here. If you want a more precise p-value, absolutely use your calculator. It'll give you an exact value. So for my two-part conclusion, I need to say whether or not I reject the p-value and the significance level. And then I need to tell how strong the strength is in terms of the alternative. So we reject the null hypothesis with a p-value between 0.05 and 0.10 at the 0.10 significance level. So it tells the reader why we rejected it. And then there is some to moderate, so this is using that spectrum we had. So some to moderate evidence that the M&M's color distribution is different than what the company claims. So we have, some evidence that at least one of the colors is distributed differently than what's claimed. So I believe that'll be it for Lesson 10. Lesson 11 is going to get at two-way tables. So we're going to basically graduate from one-way tables to two-way tables. Still dealing with chi-square tests. And I will check in with you there.